Okay, this is part 6, and we are talking about color. And color, if you remember, is a formal element of design. It is a tangible element, and it's a highly complex one. This discussion will basically be a really broad overview. It will not go at all into depth. There's a whole nother color theory class for you to take. And even in there you won't learn everything there is to know about color, but you'll learn a lot. So this is basically give you a foundational understanding, and it skims the surface, but you should come away knowing more about color than you do right at the moment. Color, as I mentioned, is one of the formal elements. It is, as I said, the most complex of those, which is why it requires a separate study. It has biological effects. It has scientific understanding in terms of it being measurable. It is definitely visual. And most of us would have a favorite color. We sort and order and classify according to color. We identify things by color, and so there is a very common understanding of color. Color is a visually dominant element. It's one of the first things that we see or understand about something. We'll look at the red ball versus the blue ball, or we'll sit in the black chair and you can sit over there in the brown one. It is a way we use color to describe and differentiate objects from each other. Color, its complexity is best understood through what's known as systematic study, which means there's an order, there is a regularity to the study, and since it's systematic, we divide color into classification systems. There's a classification system for light, and there's a classification system for color, because light and color are related. First thing to understand about color is that it is a perception. It does not really exist, and that kind of plays around with most people's heads, because we play with crayons and we do finger paints when we're kids, and everything is about color, but it doesn't really exist. It's a perception. And what happens is that light interacts with the photoreceptor cells on your retina and stimulates those cells to create opsons and send those opsons down the optic nerve to the visual center of the brain, where we interpret the yellow and the white and the green and the blacks and the grays and everything that's in this image. But it's not really there. We're seeing it, but it's not really there. Color starts with a basic understanding of light. Without light, we don't have color. If you turn out the lights, you can't see color. If you dim the lights, it's harder to perceive color accurately. So light is very much required to understand color well, to see it well. And color is actually a part of light, so it exists within light. We need a direct light source, like a light bulb, the sun, your computer monitor screen, whatever, and a reflected light source, such as a surface. The only thing that does not reflect light is something that transmits it, and that we know as being transparent. So transparency just allows the light to pass right through, and it has no color sensation to it. But everything else, anything that you perceive a color on, whether it's black or white or gray or purple, or it's brown or it's mauve or taupe or whatever, they have color, they are reflecting light. You can't see light unless you're looking directly at the source or at the surface it's reflecting from. Light is part of the energy spectrum. On one side are gamma waves, radio waves, sound waves. On the other side are microwaves and on up the scale. So light is actually energy. It's a very small portion of the electromagnetic spectrum. If you know, that's kind of Albert Einstein's sphere. It's not really ours except for that little portion that we call light. And we know it as visible light or white light. And within that there is a spectrum or a range, a gamut of color going from red to violet. And over here would be infrared, which we can't see, and over here is ultraviolet, which we also cannot see without aids to help us do that. So we have all the colors in the rainbow existing in white light. And how we understand that there is color in the white light is that we pass the light through something that's going to bend the light waves, like a prism or a piece of crystal where the light waves will bend, and you'll actually see a rainbow within that form because the light is bending and it's breaking apart. Red has long wavelengths, violet has very short. And if you're at all familiar with the computer monitor understanding or your television screen, things like that, you will pick out the red, green, and blue. These are the foundational hues in light. These are the primaries. And you can combine red and green and you'll get yellow, and you'll combine green and blue and you'll get cyan. And if you combine red and blue, you will get a color known as magenta. The reason we see color on a surface is because these wavelengths are being either reflected or absorbed into the surface. So if the surface is white, we've got white light that contains all of this. What's happening is all of this, which is represented here by the green, the blue, and the red, so here we have the red, green, and blue, is all being reflected from the surface. And if it's reflected at a high amount of light, we have white. If it's reflected at a very low amount of light, we have black. If the surface is blue, it means that the red part of the spectrum here and the green part of the spectrum are being absorbed into the blue. They're basically being filtered out, and the only thing that's kicking back to our eyeballs are the blue portions of the spectrum, so that would be down in here. If we're seeing yellow, it's because blue is being absorbed and red and green are being reflected, so that's why we'd be seeing this area over in here, and that's why we'd see the yellow surface. So we see color on a surface because of reflection and absorption of light waves. It's a filtering process. There's two different sources of direct light. Direct light is what's actually making the light. It's sunlight, it's a candle, it is a cigarette lighter, it is a campfire, it's a tungsten bulb, it's a compact fluorescent. Incandescent light is made by anything that burns, and that would include the tungsten household bulb, that would include sunlight, firelight, candlelight, things like that, anything that actually has something in it that is burning that's causing the light to happen. Luminescent light sources are fluorescent lights, whether the tubes or the coil type of bulb here. It would include your computer monitor because it's electronic, your cell phone, which is electronic. It includes things like plankton and fireflies, which are biologically sourced in terms of being original light sources. So two different kinds of direct light that we deal with. We have tungsten or the incandescent, and then we have luminescent, which is anything that is fluorescent, neon, electronic, or biological. Fluorescent and neon are both the same idea. It's chemical. Indirect light is reflected from a surface, and if we're seeing color on a surface, as I said, it's because light's being reflected and light is being absorbed. the stuff in the surface is called pigment. Another word for it would be colorant. There are natural pigments and there are synthetic pigments. Natural pigments are either going to be dye-based or mineral-based. Dye-based might be indigo, indigo. Mineral-based might be cobalt, things like that. So I know that some pigments come from red beetles and things like that. So anything that has the ability to reflect and absorb light is a pigment of some sort. One of the ways that we deal with color is through the idea of a classification system, and that helps us define, sort, organize, and figure out how color actually combines into other colors. One of the late 1600, early 1700 guys who was dealing with this about the time of Isaac Newton, a little later, was Goethe. He was a German poet and philosopher, and he actually was very interested in color and light, and actually first figured out that color was a perception. That's one of the first things that he proposed. So he had a fairly accurate understanding of how we see color, even without the technological ability to prove it. So what he did was he took the foundational hues that are actually in pigment, red, yellow, blue. Those are our traditional understandings of foundational hues or primaries. And he would mix secondaries from them, violet, green, and orange. And then he would mix directionally. So the orange with the blue would make a tertiary color, and the red with the green would make a tertiary, and so on. And so he built a color triangle in this manner, and then divided the triangle up into various segments to describe various personality types and things like that. So he was really into all this interesting, trying to find a practical way to explain color and to use color to describe other issues of life. Goethe's contribution still remains, but the major systems that we look at this point are the additive system and the subtractive. The additive system deals directly with the source of origin, the direct light, anything that's coming from your computer monitor or from your candlelight or whatever. Its primaries, as I've already pointed out, are red, green, and blue. And when you put those all together, you add them all up, red and blue mixed to magenta, green and blue mixed to cyan, and green and red mixed to yellow, all three together mixed to white, which is the entirety of the light. There are subsystems under the additive, and that will include things like C-Lab, CXYZ, HLS spectral, and RGB. Don't have to worry about what all these are or what they mean, but just know that there are systems within systems. And the additive system pertains to direct light. Subtractive, that system pertains to anything containing pigment, so it's reflected light. And anything that deals with printing, graphics, fashion, interior design in terms of fabrics and paints, natural colorants, inks, silk screening, anything like that is printed. Its primaries are the traditional red, blue, and yellow, or the scientific understanding is magenta, cyan, and yellow. Systems include Itten, Munsell, Ostwald, Goethe, Holzel, Chevreul, and there's several others. And you'll probably become most familiar with Munsell and with Itten. Itten is the one that's most commonly used. Itten, by the way, was a friend and fellow of Joseph Albers in the Bauhaus days back in the early part of the 20th century. Itten's system consists of 12 hues, A hue is a color family. It would be like the Smith family. And so you have the Smiths, and then you have the Jones living next door, and then you have the Martins and the Tanakas and the Cohens and so forth, all the way around the cul-de-sac in the neighborhood. So we have a red hue family, we have a yellow and a blue hue family, and these are hues. These are your primary hues. A primary hue is a foundational hue, and foundational means you cannot achieve it, you cannot mix any two colors to make a primary. You start with a primary and you make all the other hues and all the other colors that exist. So you can't make a blue by mixing two other hues. You use blue and you make colors from it. Secondaries are a mixture of two primaries. In the 12 hue system, that's going to give us orange, violet, and green. And they're considered compound hues because they contain two primaries, two simple hues. Then if you mix a secondary with a primary, you end up with a tertiary. And those are the compound hue names. So we have compound hues with hyphenated hue names, and we have red-orange, red-violet, yellow-green, yellow-orange, blue-green, and blue-violet. So those are your 6 tertiaries. It's technically correct to say red-orange rather than orange-red, and blue-green rather than green-blue. And those are your 12 hues. And remember, hue is like it's a family of color. On the 12 hue system, there are complementary hues, hues that sit across from each other, and it's spelled with an E instead of an I. And so we have yellow and its complement directly across violet, and red and its complement directly across green, and then blue and its complement go directly across to orange. And if you mix orange with blue to the point where it's neither orange nor blue, you get this middle color, which is really close to black, but it's actually really dark. It's darker than charcoal gray. It's not a true black. If you're in the Los Angeles area and you're familiar with the La Brea tar pits, it's kind of that La Brea tar pit color, that kind of murky, really dark, dark gray, but it's not totally black. So this is a neutral. You have the hue mixed with its opposite, and they neutralize each other into this gray. And if you've ever done watercolor and you have had the misfortune in your trying to learn how to work with watercolor where things get muddy, they get muddy because they're neutralizing, because you're mixing the colors into each other so that they get muddy, they get gray. So every hue has a complement. And in the complementary pair, say yellow to violet, you have the full range of the 3 primaries, because violet is made up of red and blue. So with yellow and violet, you have yellow, red, and blue. And that happens with any complementary pair. In the subtractive system, white is the absence of chroma, or the sense of color, and black is the sum or the total mixture of all chroma. A color is chromatic if it has a sense of having color. There are achromatic colors, which would be black, white, and gray. Chromatic colors are identified with particular hue families for the most part. We get browns and earth tones by mixing complements together, and before we get to that murky tar pit gray, we get what are known as earth tones, and they can be greenish, bluish, or reddish, yellowish. There's like a mossy green, a sage, things like that. These are all earth tones. Some of you might be familiar with yellow ochre. It is a earth tone. It has been mixed with its opposite hue. And so earth tones therefore come from mixing hues together. But you're mixing not around the hue circle like going from a primary to a secondary to a tertiary, but you're mixing across. And you should be picking up now, of course, a circle is a geometric device, and you can go around the circumference or you can go across the diameter. So there's a lot of geometry involved in this understanding. Value we've touched on several times so far throughout the course of the quarter, and value is our ability, it's by value contrast that we can see a form, lightness versus darkness. And so value is the idea that color has lightness or darkness, and we can lighten any color by adding white and reducing the value, or we can darken it by adding black and increasing the value. And I've taken the hue circle from the previous couple of slides and have translated it into a grayscale. And so we see that yellow is not as light as white and violet is not as dark as black. And we see all the respective hues at their normal value. Like I said, to lighten you add white, and to darken you add black. So one thing to understand is that both color, chroma, which is the sense of having color, and value, which is the lightness or darkness of any given color, are understood in our perception based on what is around them. We never see color in a vacuum. We never see it without an environment. And so our color perception, our light-dark perception, is very much influenced by what's surrounding the color that we're looking at. So we have a grayscale here, and we have a grayscale here. And this strip appears to be darker on this end and lighter on this end. This strip is the same color, and it's close in value to this middle gray. The reason it looks lighter over here is because it's on a darker ground. The reason it looks darker is because it's on a lighter ground. So notice figure ground perception really strong, really strong. We get the lost contours, the lost boundaries right in here. So figure ground perception is not strong. And then I've taken a violet and tinted it, and it's the same value as this strip up here. It's the same. If this were translated into gray, it would look like this. But you see that it looks darker here on the lighter ground and lighter here on the darker ground, and right in here, again, it's struggling to be seen. It's a little more visible than the grayscale version, but we're still losing boundary. So when values are close together, figure ground understanding is really reduced, and that's a very important thing to understand. The ideas of pushing and pulling again. The ellipses are all the same color. On a darker ground, the ellipse will pull forward. On the lighter ground, the ellipse will appear darker and pull forward. Where there are similar values going on between the ellipse and its surround, the ellipse tends to try to sink into the background. This is called pushing. It's pushing into the background. This is pulling forward. This is pulling forward. And again, the ellipses are all the same color, although they don't have the appearance of being the same color.